All right, good afternoon, everybody. Hope everyone's having a great day. Let me get my screen started here. I'm not sure why this isn't, hold on one second. Here we go. Oh, hope everyone's having a better start to their day here than me. Want to thank everyone for joining us on today's webinar. We're really excited to have Milan Heninger with us today. He's going to be talking about the use of ultrasound to detect inverter-induced power quality issues. This is a presentation that he actually did for us in May at our Ultrasound World Conference. And so we thought it'd be a cool way to have him share this with a wider audience, folks who weren't able to join us down there. And also for those of you who have, thought about coming to our Ultrasound World Conference before and haven't been able to, this is just a great example of the kind of content that you can expect to hear at our event. So kind of killing two birds with one stone here with that. Before we let him get going, I just want to go over a couple housekeeping items. We are recording this. Milan was nice enough to allow us to do that. So we will put this recording up on our website a little bit later this afternoon. So if you have to hop off or you want to reference it again, you'll have that ability to do so. And we, of course, welcome questions. There's a questions box, so you can type those in, and I will see those, and I'll get those tossed over to him as we go through the presentation. And, of course, we'll have some time at the end for some questions then as well. So feel free to interact as best we can on this forum. Just also like to always point out, we are doing this live, so if we have any audio issues or internet issues, just bear with us. We've got a few, things in place to hopefully work as backups, but, if we need to pause and fix anything, we'll do it just as quick as we can, but just kind of part of the fun of doing these things live. So, excuse me, with that, I'm going to turn the screen over here to Milan and let you get going.
Thanks a lot, Maureen. Hopefully you guys are seeing the start slide to this presentation.
Yep,
first of all,
great.
Fantastic. All right, so first of all, I just want to thank UE Systems for giving me the opportunity to present on this topic. I think it's an important one. And a lot of people in industry, we use inverters every day. We just don't really understand sometimes how they work or the consequences of installing them on systems that weren't specifically designed for it. So before we get going, just a little bit about me. I have a bachelor's degree in mechanical engineering. So why is a mechanical engineer talking about power quality issues? We'll get to that in a second, but my background is I started out as an electrical technician doing startup and commissioning on power plants, ethanol plants, and things of that nature. I started, realizing that I wanted to get even more technical, so that's when I went back to school to get my mechanical engineering degree. And now I work for Enel Green Power as their senior technical support manager for our geothermal and solar operations and maintenance group. Basically, it's plant engineering and maintenance planning. Right now, I'm also working on a MBA with an emphasis in renewable energy policy, and I take care of my family. So I've got 2 little ones and my beautiful wife. So this is one of our flagship facilities. It's located in Nevada, and this is why I have a lot of experience with inverters. So this is what we're actually looking at here. The heart of the plant is a 33 megawatt binary cycle geothermal facility. We use inverters from a 480 volt all the way up to 5 kV native for running electric submersible pumps and fans and various auxiliary equipment. And then we have a large photovoltaic field out there, over 50 megawatts installed, polycrystalline and amorphous silicon. And those inverters are taking the DC energy and converting it into AC. And even in our CSP field, concentrated solar, where we take the sun's energy and use it to heat the brine for our geothermal process, there's a VFD that's running a circulating pump out there. So we deal with this stuff literally every day. So before we can really get into the details of how ultrasound can be used for detecting issues with an inverter, we have to understand 3-phase power. And since we have probably a pretty diverse group here, almost 70 people on, I'm assuming that some of you may need a refresher, so we'll get into that. So when we talk about three-phase power, we know that there's 3 wires typically, and those are being represented here. So you've got A, B, and C phase, or red, green, and blue, and it's a nice, smooth 60 hertz waveform. Each waveform is 120 degrees from the other one, and we'll get into more detail. But what is your equipment experience? So I'm going to go ahead and give you an example here by putting this little boat up and sending it for a ride on this wave. And you can see that it's a nice, smooth waveform. It's comfortable. The equipment likes it, and it can easily tolerate this type of environment. So we can look at the time waveform like we did, or we can look at it in this vector plot. And what we see is that at any instant in time, we can take all 3 phases, add them up, and it'll equal 0. And we do that with vectors in what they call the tip-to-tail method. And you can see that the arrows all converge with one another. And similarly, we can look at currents and magnetic fields the same way. So if we were to just convert these to magnetic fields, you can see that the center of the magnetic field exists right in the middle of the rotor of this imaginary motor that I drew on the screen. So now that we have that basics down, we can start looking into what pulse width modulating machines are and how they function. And this is just kind of another cool picture of the facility. So now, the very key inverter components, it all really starts with the solid state device. And we take DC power in, we do some magic to it, and we create AC power on the backside. At no point are we actually generating any electricity. It's just changing its form. And the way we do that is using an IGBT, which is an insulated gate bipolar transistor. And this is really just a high frequency switch. It goes on and off really, really fast, and that helps us create that pulse width modulating waveform. So they're managed by a gate driver, and all that is doing is putting electricity into the silicon of the IGBT, and that allows the current to flow through from the DC input to the output. So this is really the smart part of the circuit, and the IGBTs, they switch at really high frequencies. So when we're talking about electricity, we're normally talking about a 60 hertz fundamental in the United States or 50 hertz internationally, but the IGBTs are switching at 2,000 to 9,000 hertz, so much, much, much faster. The way that it does this is it takes the DC in, so in my drawing, it would come in from the left, and it goes through typically 6 at minimum of these IGBTs, which then are able to convert that into a simulated AC waveform as they're switching on and off. And we do that with pulse width modulation. And that's what the switching pattern is called that you can see at the bottom of the screen. Basically, by changing how long those IGBTs are switching for, we can cause the voltage to raise and lower. So by changing that switching pattern, we're able to change the frequency, the voltage, the amps, even the power factor. In our solar inverters, we can have them run at unity, so a power factor of 1, or we can reduce it to whatever the utility would like us to have it set to. But we have to add one more thing, which is a filter, and that helps simulate that sine wave that the perfect AC component would look like. So I've been talking about just a simple inverter, but let's go ahead and expand to what's probably in most of your facilities, which is a VFD or a VSD, so a variable frequency drive, variable speed drive. There's a lot of different names in industry, but they're all typically the same device. And the first thing that we do is we take in 3-phase AC with the rectifier. And all that is doing is it's just breaking up that AC component and forcing it to be DC. And once we've converted it to DC, then we're able to convert it back into AC at the frequency and the voltage and power factor that we want it to be, which we use to power our motors or whatever load we want to put on there. So this is a theoretical example of what pulse width modulating waveform would look like. This is assuming a perfect inductor. Otherwise, we wouldn't have those flats because the actual voltage and current would fall away as we shut off the pulse width. Now, this is the ideal, and the next picture I'm going to show you is a real world voltage waveform that I actually collected in the field on some of our 5 kV equipment. Suddenly you can see that this does not look like that nice 6-step waveform that you saw before. Instead, it's pretty aggressive looking, especially when compared to that ideal sine wave. So what we're going to do here is we're going to put our boat back on here, and now we get to talk about what your equipment is experiencing as it's riding these waves. This is not a comfortable situation for most equipment. This is why we have inverter duty motors. This is why properly designed VFD systems actually have special cabling, insulation, and things of that nature. This high frequency is tough on equipment. And if you look really closely at the waveform, you can see that it's not a perfect sine wave. Even if you were to eliminate the high frequency component, it's just a good approximation of one. So we're going to go through the vector diagrams again, and just by grabbing an instance in time, and we're going to go ahead and show what that plot looks like. We no longer have a balanced case. So when we take those different vectors and add them up, you can see that it no longer equals 0. So some of you may have heard of what they call a zero sequence voltage, and that's what the black arrow represents. That is the voltage or the currents that are being used to balance out this situation, so that way the sum is actually 0. And if we were trying to measure this, that could be considered leakage current, or there's a few other things that it could manifest itself as. And we'll do the exact same exercise, but looking at the current or the magnetic fields as a result of the current. And again, our magnetic field is no longer centered on our rotor. Instead, it could actually shift all the way over into the stator. This is where you start to see a lot of the interesting things like bearing fluting and some of the other manifestations that are really typical in improperly set up VFD systems. It's by creating this non-zero vector sum where we're shifting magnetic fields, and that creates a potential between the rotor and the stator. So the only way to fix this is to clean up the power. Now, since this was for an interactive presentation in the past, I asked everybody who has had reduced life on their with VFDs. And most people think about motor life, but we really have to go one step beyond that and start thinking about our transformers and splices and cabling and communications. And there's a lot of other nearby equipment that can actually be affected by your VFD. So let's talk about why. So there again is something that we sampled. You can't get this kind of resolution on a typical power quality analyzer. Instead, we use oscilloscopes and capture this sort of data. And what we can actually see here is the rise and fall as the IGBTs fire. And in the very first case, hopefully you guys can see my mouse, but if not, I'll go ahead and highlight this for you. You can see the ringing. So in the very first box, we were actually trying to get somewhere around 1300 volts, and the spikes can get all the way up to 2500 volts. This continues as we move up the waveform every time those IGBTs fire. And this ringing is part of the reason that we have that non-zero vector sum and we add up all three phases. So in the electrical parlance, you'll hear people call this ring waves, and that is created by the IGBTs. So I just went ahead and showed you what a wave of any type could look like on the right. And it's important to understand that these ring waves are reflective. So when you hit a splice or any kind of electrical termination, a hard, tight winding in the stator, things of that nature, you can get that high frequency component that will start to reflect back. I'm gonna go ahead and show this with a phase shift, just so that way we can get a better idea of, I'm sorry, not a phase shift, but actually with a frequency change, a very small frequency change. So that way when we add and subtract these waveforms as they're coming together, you can see that we created beating. So those of you that have maybe a vibration background, this should be really familiar to you. This exact phenomenon can occur with electrical waveforms. Now, clearly, we started with something that maybe was only 500 volts above design. But when we add these waveforms together, we can now get to 1000 volts above design. clearly this is going to attack insulation. It's going to cause damage to the motors. The magnet wire isn't going to be able to handle it. And it also increases the heat within the motors as well, and cabling. So this is high frequency, and it's therefore very high stress. So heat is one part of it, but you can also think of this as a hammering effect. So every time you have one of these spikes, it's actually beating on the insulation of your motor and your electrical system at large. And it can also lead to mechanical problems where you can have like shaft breakages due to torque issues that are being created by this high frequency content. Now, one of the most important things to understand here is that your dielectric strength is inversely related to frequency. So we kind of understand this intuitively. If any of you have played around with a insulated screwdriver, you'll see that they have a higher voltage rating DC than they do AC. So when we start talking about running our frequencies up another order of magnitude, so from 60 hertz to 6,000 hertz, obviously the dielectric strengths are going to go down. And this is why we start seeing cabling issues, insulation breakdowns, and arcing and tracking and things like that inside of bearings. So I would like to show you some manifestations of what this type of problem can cause inside your equipment. This is a really textbook case of bearing fluting. This is on a roller element bearing, and you can see this washboard pattern. The root cause of this failure is not a bearing problem. It is an electrical issue. So I talk about this as the leaves and the roots. This is kind of stealing a quote from Thoreau that, for every 1,000 people that are, and I'm butchering this, but for every 1,000 people attacking the leaves of a problem, only one is attacking the root. And that's what I really want this presentation to be for you, is to kind of help you understand this so that way you can go after the roots of the problems in your facilities. Now here's a less typical case. This is coming out of a oil-filled motor from an electric submersible pump. This one I personally tore down and harvested some of the components because these are a really great example of what this type of problem can look like. So since this is oil-filled, the oil is actually partly a dielectric, and it's a lubricant as well. So what we believed was going on here is that due to the high frequency content, it created again, a non-zero vector sum, creates a potential, and was actually causing copper plating on what would normally be a very shiny brass colored sleeve bearing. We call this frosting, and it almost looks like it was sandblasted, but it doesn't happen very evenly, only in places that you have very tight tolerances. So we're going to zoom in a little bit, and this is what that bearing looks like under a scanning electron microscope. So at 50 times magnification, you can see that there's a relatively smooth surface, almost no striations, but then there's like the surface of the moon look. And at 500 times magnification on the right, you can clearly see the melting that was occurring from the electrical discharge inside this bearing that was directly caused by an inverter. So people talk about harmonics and all the other characteristics that we can see. These are all types of things that can occur from an inverter. So we'll just step through these. So first of all, the characteristic of the impulse and reflections. This can cause electrical and mechanical failure. As I said earlier, you can create torques inside the motors, you can damage bearings, and then you can also attack insulation and things of that nature within the motors as well. So you'll have shorts, usually on end turns and at splices or near splices. But if you get to really long cable lengths, like in the case of an electric submersible pump, where you can have surface cabling in the miles, and then downhole cable, which was, in our applications is about a 1/4 mile, but can be up to 10,000 feet or more in the oil fields. This could occur in the middle of the cable, where for no apparent reason, the cable insulation has blown out, and everyone chalks it up to well conditions or to mechanical damage or something like that. But they didn't look at the whole system. Because we have to remember that another aspect is that this high frequency doesn't change direction well. And that's part of this. So it wants to reflect if it hits anything. And if it's going around tight corners, as in a stator of an electric submersible pump or other types of motors, then you'll typically see some kind of stator failures there. And then also in splices, because it wants to reflect there back, and you get the amplification because those waveforms start adding onto each other. Now, this is getting a little bit more into the physics, but this high frequency travels over the wire, not really in it. And we talk about this even in 60 hertz, but the lower the frequency, the deeper into the wire that electricity flows. So in this really high frequency stuff where we're talking 5,000 hertz or so, you create skin effect heating. And I have personally seen where the jacket or the insulation on a wire has disconnected from the conductor inside of it because of this. We were sitting there kind of scratching our heads for a little while, and then we started talking about it, and we realized that this was most likely being caused by an inverter. Now, from a business perspective, this high frequency actually adds to your system current. So on some of my electric submersible pumps, they operate at about 165 amps at 4160 volts. And we're able to filter off over 20 amps of high frequency current in that motor. And we do that by putting on sine wave filters and common mode filters to eliminate all of that high frequency content, well, as much of it as possible. But the consequence of not handling this is it degrades your power quality, it increases the heat, and it increases your cost to run that equipment. And electricity isn't cheap. And when you're running a lot of variable frequency drives and you're running a lot of motors, this can really become pretty substantial in the cost of operations for your facility. We're gonna talk about capacitive coupling. Now, this is what everybody thinks of as electrical noise or induction. And what we see is that as we increase our frequency, we also increase our capacitive coupling. And in our case studies that we're gonna talk about here in a few minutes, you'll get an idea of how this can manifest itself. But we all know that we should keep communications cables away from our AC power cables. But sometimes that's not done as well as it could be, or it's done under the assumption of only 60 hertz. And the clearances, when you start getting into this real high frequency stuff, needs to increase. And then finally, insulation. So as our frequency goes up, our dielectric strength goes down. And this leads to shorts and fluting, EDM, which is electric discharge machining, which is another way of describing that bearing fluting that I showed on that copper and brass colored bearing. So your insulation is constantly under attack when you have this high frequency component. So now we're going to talk about how I've experienced these phenomena in our facilities. And then the first one is on ESP failures. And then we're going to talk about a little bit about remote sensing and inspections as well. So what is an ESP? It's probably one of the most unusual motors that some of you have ever seen. In our case, there's two 750 horsepower motors. They're connected in series, and they operate in a 300-degree or higher ambient condition because they're a quarter mile underground hanging on a pipe. As I said before, these are oil-filled motors, and we call them tandems. So they share a single shaft to drive a pump to be able to lift fluids from underground in our geothermal reservoir to the surface so we can use it in our binary cycle geothermal process. So the aspect ratio on these motors is really unusual. It can be like 40:1. Most of ours are 8.8 inches in diameter, and they can be well over 50 feet long. And that's a 1,500 horsepower set of equipment. So you can easily have about 20 or more bearings per motor. And this is especially relevant because most of your inverter duty motors are designed with a couple of very important tweaks that have been done. Usually one of the bearings is either a non-conductive or insulated, and that helps reduce the likelihood of having circulating currents inside the motor. The iron to copper ratios are also different than we can do within an ESP, and the insulation is typically higher rated to be able to handle that high frequency content as well. ESPs, because of their very extreme form factor, extreme operating conditions, we cannot do the things that you would do to a surface motor in order to keep it safe when operating on a variable frequency drive. So these are some of the things that we were seeing. We had bearing frosting or fluting, copper plating inside the motor. We had end-turn failures on our stators, and we had cable insulation adhesion issues, splice failures at our wellhead penetrators, things of that nature. We also had some situations where instrumentation wasn't functioning very well at the wellhead either. So we started doing power quality analysis, brought in some subject matter experts, looked really closely at our electrical waveforms, and we realized, okay, we need to install these sine wave filters, but more importantly, we also have to install a common mode filter as well. The reason for that is that the sine wave filter does a good job of knocking off most of the high frequency content, but there's still usually about a half an amp or so still on the waveform. And this doesn't seem like a lot, but we've, through multiple cases, we found that more than 1.3 amps of high frequency content, so this common mode, which is the high frequency content that's going from the line to ground, can cause a lot of issues inside those motors. Primarily, in my case, it was bearing problems, but overall, it just results in reduced run life. So we were out doing one of these power quality analysis and testing, and we had taken the system back to the way it was originally commissioned. While we were there, I was using UltraProbe 10,000, and I was listening to the wellhead junction box. And what I noted was that I could hear the inverter, which was interesting. We started thinking about that a little bit, and we continued with our testing. We installed the sine wave filter, and what we noticed is that the intensity distinctly went down of that inverter noise. Now, why is this happening? This wellhead junction box is a mile away from the inverter, and we really had to start thinking about that. And then when we installed the common mode filter, it was gone. So to reiterate, using ultrasound, we were able to hear the inverter. As we added filters, every time we added a filter, the intensity and the magnitude of that high frequency content that we could hear from the inverter diminished until it was undetectable. So why were we seeing a change in ultrasound? So before, on the left, you can see all that real high frequency content. On the right, you can see what it looks like with just the addition of a sine wave filter. So there's no common mode filter installed here. And if you look really closely, there's still a lot of small peaks along that waveform. That's the common mode. And that's what we were taking off with the common mode filters. But because the common mode wasn't installed, there's still a high frequency component there. So what this did is it gave us an indication as to what was going on. So by scanning these 5 kV armored cables, so that has a metal jacket around the outside, with the UltraProbe, we could record these waveforms, and using this data, we could determine which wells were in the worst condition. Now, what we were actually measuring was the electricity leaking through the insulation of the cable and finding a path to ground. And as most of us know with our ultrasound training and background, that when you have arcing, an electrical phenomena, it causes ionization of the gas, and that's what we actually hear, is the turbulence caused by that ionization. So in this particular case, we were listening to the leakage, finding a path to ground, and ionizing some gas along the way. And that's what that little graphic on the right is indicating. And then the other thing that we started doing is, this is very ESP specific, but we're using a stethoscope probe on the wellhead, and we can measure the machine vibration that's 1,700 feet downhole. I liken this to a 60,000 pound guitar string, and we're just standing at one end of it listening. People that work around ESPs, you can frequently tell from the wellhead that the motor is doing well or it's not doing well. So we started collecting this data, and we're now performing spectral analysis on it, trying to look for changes. We may even go so far as to feed this into artificial intelligence, because with 14 or 16 rotors inside each motor, we can have a lot of forcing frequencies. So subject matter experts analyzing this data is very difficult. I don't have any great results to show you guys right now because we're very much in the science experiment stage of that. But hopefully in a year or so, we'll have some pretty conclusive data. Our second case that we're going to talk about is solar instrumentation failures that we've been suffering at some of our photovoltaic facilities in Minnesota. So we're investigating this right now, but some of the symptoms that we're seeing are that our Modbus instruments are losing communications in the morning and the evening. And what we're suspecting is going on is that in the morning and evening, the inverters are very lightly loaded. And inverters that are lightly loaded have higher harmonic content. And the higher the harmonic content, the more induction that you're going to get, the more electrical noise you're going to get. And the mistake that is frequently made in the solar world is that everyone assumes that your DC cabling is exactly that, that there's no AC component there. But the reality is that, you know, as if we took a valve and we're turning it on and off pretty fast, not only are we changing the waveform and the flow or the case of that water downstream of the valve, but you're also causing problems upstream. It's just the same as the water hammer effect, or, you know, when you're dealing with water systems. So in this DC case, the switching of the IGBTs actually causes an AC component on the DC cabling. So we therefore kind of suspect that inverter line-side harmonics are a real possibility here. So we're setting up a testing program right now to take a look at our waveforms on the DC cabling. Ideally, it should be a straight flat line, but I think when we start looking for AC components, we'll probably find it. And another thing that kind of is leading towards this is that we noticed that with a non-modified or an unmodified ultra probe, that we were getting a lot of electrical interference, and it was actually showing up in the spectral analysis. So we've added some shielding and ferrite chokes to that in order to eliminate that problem. And again, this is inverter induced. So even your tooling can have some adverse effects from these inverters. So our next steps in this science experiment is, as I already mentioned, we added significant shielding and chokes to our ultra probes for solar applications. And we're now using ultrasound to inspect our DC combiner boxes at similar loads. By listening to those waveforms, we might be able to get an idea of what's going on with the inverter from the DC cabling. Inside the inverter cabins, there's a lot of competing ultrasound, so we're trying to find somewhere else in the system to get a good look at how those inverters are functioning. We want to use ultrasound and oscilloscopes to measure and quantify our harmonic content, so that way we can come up with some way to mitigate this. So it could either be filters, adding chokes to our DC cabling, or, you know, some other solution in order to reduce those harmonics. And the third case that I want to talk about is one that's probably more applicable to the day-to-day for the majority of facilities that we're all working at. But I first wanted to let you know what we found. So we were doing our standard dissolved gas analysis, and we saw that 6 of our 8 station transformers had overheating and arcing activity inside there. All 6 of these provide power to variable frequency drives. Over 2/3 of their design load is going to only 2 VFDs. Now, when you start talking about waveforms that are not exactly the same, and we know that inverters can cause line-side harmonics, we believe that what may be going on is that we have the addition of these waveforms, which is attacking the insulation inside of our inverters. So in order to test this, we went ahead and used our contact probes, or the stethoscope probe with the ultra probes, and we listened to the inside of our inverters. Now, I know that UE Systems does not teach this as a technique, and you have to be very careful when doing this, because if whatever you're touching is not grounded, you could create a path through the device and your hand and your body, and you could be shocked, which is the main reason that they don't do that. So I'm not 100% advocating that you do this. I'm just saying that if you're going to do contact measurements on a transformer, you need to make sure that it's properly grounded, operating correctly, and that it's safe to touch with a bare hand. So looking at these waveforms that we collected with the UltraProbe 10,000, we could see the inverter carrier frequencies in addition to the active faults inside the transformer. So our next step is we are using the ultrasound again and our dissolved gas analysis to prioritize our work. We have to get these transformers rebuilt, and which one needs to go first? Well, clearly it's the one that's in the worst condition on the DGA and on the ultrasound. And then we're going to repair these transformers, and then we're going to add some more load reactors to the system in order to help eliminate some of the high frequency content. So this last case, we're still kind of looking at this as an emerging problem. But what I'd like to just let you guys know is that even your UPS systems that you use for emergency backup power are literally just a battery powered inverter. And we were having some situations with some solar contactors opening up randomly. And those solar contactors are designed to go on thermal load only. But looking at the operating condition of the inverter, the ambient temperatures, loads, and all that kind of stuff, it didn't make sense that these contactors would be opening up. So what we're doing is we're going, okay, well, maybe we have some skin effect heating inside those contacts, and that could be causing them to open somewhat randomly. So what we're doing is we're testing by looking for phase imbalance, harmonics, and low power quality coming off of these UPS systems. And what we are finding in this case is that these particular UPSs are causing some problems for us, and we're just continuing with the testing to come up with a good case on how we want to replace and repair this problem. But ultimately, we have to do some more research. So we can take a bit of a breath here and think about the highlights of this conversation. First of all, inverters have IGBTs, and IGBTs are just high frequency switches. These high frequency switching creates imbalances in harmonics that lead to failure modes that you may not have experienced before. I've talked with a lot of people who said that for power savings or energy efficiency, they've installed inverters on old systems, and then their mean time between failure just got dramatically worse. They then were blaming it on lubrication or something like that, but look at the system. Because a proper design of the system can reduce or even eliminate these harmful transients. You know, the whole point is we can't eliminate it 100%. We just want to get it down to a point where your equipment can safely handle whatever harmonic content is still on your electrical waveform. And most importantly is realize that this impacts your entire system. This impacts the line, your load, your cabling, your motors, your transformers, nearby systems, instrumentation, your tools. This can really get weird. And this is because the high frequency content does not operate the way that our normal 60 or 50 hertz frequencies electrical signals would. So you have to kind of teach yourself what this high frequency stuff can actually cause within your systems, and then come up with ways to measure and mitigate. So from an ultrasound perspective, this high frequency electricity can create ultrasound while as it's trying to find a path to ground through ionization of gases. So if you can hear an inverter where you didn't design for it, you might have a problem. And again, think system, not component. If you have a motor failure, but you're on a VFD, you really need to think about the VFD. Could that be a cause for your failure? If you're looking at something that's even on the line side of your inverters, could there be a connection there? I highly, highly recommend that in those sorts of cases, you look at your power quality very closely. An oscilloscope is a great way to do that, but a really good power quality analyzer with appropriately selected current probes will give you a good idea. We can also, it appears that we can also use ultrasound in remote sensing applications for both mechanical ultrasound in our electric submersible pumps, and then also on looking at our inverters for our solar applications on the DC circuits. And by using a trend of the performance of the inverters, we may be able to use this for failure predictions. So we're at about 36 minutes, but that's kind of the gist of what we've been doing at Enel, and looking at the use of ultrasound in all of our inverter applications. And we're using it across the entire board, from our mechanical pumps to solar inverters and UPSs. So with that, I'd like to hand it back over to Maureen, and if anyone has questions.
Great, great. Yeah, we've had a few come in, so we'll toss these to you here now. So someone was asking with the UltraProbe 10,000, what setting you had it at when you were listening to your VFDs?
Yeah, so in that situation, we were using your standard electrical inspection technique. So it was set at 40 kilohertz and maximum sensitivity.
All right,
Using a
cool. And
scanning
actually,
module. Yeah.
oh, yep. And that just came in actually a second time, so that was a big question. And then a couple people have kind of asked sort of similar questions about like wanting to actually hear some of these sound files. So I was trying to explain to people the sound files just they don't know, it's not very reliable trying to play it through this GoToWebinar system that we're using. So Milan, maybe we can figure out offline, like you sharing some of these sound files, that we can maybe figure out a way to put them online or email them out or something, so folks can get an actual listen to some of the things you were describing. So bear with us, folks. We'll see if we can do something about that, but that's kind of why you weren't getting to hear specifically some of the examples. So that wasn't really a question. That was more just, let me just throw that out there to folks. So okay, back to actual questions. So someone was wondering, do you have the spectral analysis of what the Ultrasound 10,000 was showing you before and after installing the two filters, the send wave filter and the common mode filter?
I don't have it to show right now, but what we have seen is that the spectral analysis shows a peak near the inverter carrier frequency, and that as you put the filters on, the magnitude of that drops, and you also kind of sometimes will see a small shift as you start knocking out certain high frequency components.
All right. And were all your VFDs the same topology, and do you think that would make a difference?
Absolutely, the topology of your VFD is going to have an impact on this. So my medium voltage VFDs are all identical. They're all a multi-level VFD. So they have 3 IGBTs or cells per phase that are helping create this. So it's a little different than some of your older VFD technology. This is a kind of a little bit better in design. But actually, as you go to the older, like 6-step type drives, you actually can make the problem even worse. So what I was presenting is almost the best case scenario. And if you go with a really cheap inverter, you can really lead to some issues. Now on the load, this is all load side that I'm just talking about. Now on the line side, there are other types of VFDs that have what they call active front ends, which is basically another little VFD that is helping mitigate the harmonics on the load side of the inverter. That could certainly change things. In my situation on the transformer faults, those are all 480 inverters. I do not believe they have active front ends, and that's probably a leading issue with that, but they are identical. So we're in this whole talk, I've only been talking about maybe 4 different types of topologies, but every time I had an issue, they were identical inverters.
Cool. All right. Can the ultrasound spectrum indicate which IGBTs may be in a failure mode for trending purposes?
The specific IGBT, I don't believe so. I've never looked that closely at it, but my intuition is telling me probably not.
Okay. Oh, wait, one more. Hold on a second. Let's see. Are there different qualities of wave filters in the market, and could the design of the filter give a false confidence that the problems are solved?
Absolutely. Your most basic sine wave filter is what they call an LC, so it's just an inductor and a capacitor on each phase. The inductors are in line, and then the capacitors tie the 3 phases together. And if you don't get your inductor size and your capacitor size appropriate for the application, so you need to look at the inverter, you need to look at your cable lengths, because the cables themselves have a certain capacitance and inductance that needs to be accounted for, and then your loads, your motors, or whatever you're running, those also need to be accounted for. And I have seen in my career situations where those sine wave filters were not appropriately designed, and instead of reducing the problem, they actually put the system into resonance. And when that occurred, it went into electrical resonance, the voltages and currents start to run away, and it starts tearing things apart. Your weakest link is going to fail pretty rapidly. So getting high quality equipment that's well designed for the system and the application is absolutely critical.
Okay. And a couple people asking again about recording it and everything. So we did record this, and I will get it up on our website on uesystems.com. We'll get it up there a little bit later this afternoon. If you specifically want to, know exactly when that where that link is and when it's up, just shoot me an email, and we can get that to you. But it'll be under our webinar section on our website for those who are asking. So, okay, all right. And if anybody has additional questions, he's got his email address up there. You guys know how to get in touch with us. So just either, make note of Milan's email, get in touch with us. We can get you in touch with him, and so forth. So don't feel like once this thing is over that the conversations have to stop. So feel free to definitely follow up with us, especially as you've had some time to digest the information and think it through a little bit more. But thank you so much, Milan, for doing this for us today. Just, want to again make note that this was a presentation that you did for us down at Ultrasound World back in May in beautiful Clearwater Beach, Florida. So just a great kind of example of the kind of information that's being shared by your peers at that event. So make note of that, make note of these dates, so that hopefully folks can make a point to join us next May and see more of this great content. But I guess with that, I'm going to let everybody head on their way. We'll be in touch with more information about upcoming webinars. We've got a whole fun month for September, our typical STEAM Timber month of webinars and resources all to do with STEAM. So if that's something that you guys have at your facility and need some help on, we're going to have a fun time talking all things STEAM for September. So be on the lookout for invites. And Milan, thanks again, and everybody have a great afternoon, and we'll see you here next time.
Thanks a lot, Maureen. I really appreciate it.